Hey, thanks, Laura, and thanks to the organizers of this program again for the invitation. It's been probably a couple of years since I've been in person. And yeah, so I'll be talking about a few different projects I've been involved with, both in terms of physical stochastic parameterization for weather prediction applications, as well as some recent projects on machine learning for stochastic parameterization, as well as ensemble prediction. Thank all my collaborators. Mainly would like to highlight Will Chapman and Tim Higgins, who are two grad students I've worked with, two excellent grad students, and David John Gagne, who's a scientist at NCAR, who have led the machine learning projects I'll talk about. So the motivation is to improve our, is there a pointer I can use? Or just the mouse, I guess. Yeah, I think the mouse. Yeah. Okay. The motivation is we would like to improve our probabilistic prediction from weather all the way to climate timescale. So thinking of it as a seamless problem, and likely and hopefully the uncertainty on short timescales of minutes to hours is small. That's what is shown in these orange lines. But as we go out further into subseasonal or seasonal timescales and out to climate timescales, which is out here, the uncertainty also grows. So we need both accurate predictions, but also accurate predictions of uncertainty of our forecast and all these timescales. And the reason is there are many different applications that use information on these timescales. So how do we generate this forecast, but also uncertainty? So I'll talk about representing uncertainty in our models with, which is the first half of the talk is on stochastic parameterization that's currently used and has been used over the last couple of decades for representing uncertainty in forecast systems. And I'll briefly show the impact of stochastic parameterization on forecasts. And then I'll talk about machine learning projects. One of them is on stochastic parameterization in an idealized setup, and then post-processing both for deterministic forecasts and also probabilistic ensemble prediction. And then the final project will be on atmospheric river changes in climate simulations from a large ensemble setup. So that'll be the last part of the talk. So there are two main sources of uncertainty in our prediction systems. Especially on the weather timescale, the initial condition uncertainty is key. In chaotic systems, if we want to predict them, we should represent the uncertainty in our initial conditions accurately so that they are projected forward. But eventually, as we go out into longer lead time, the initial conditions influence will not last. The other kind of uncertainty is the model error, which is error in representation of physics in our system. And yeah, I think almost all the talks today talked about subgrid scale parameterizations and errors in subgrid scale parameterization. So both we need accurate representation of these subgrid scale tendencies, but also the uncertainty in our subgrid scale physics. So that needs to be represented accurately to generate uncertainty in our forecasts. So this is a cartoon showing what is currently being done in terms of representing these two uncertainties. Initially, we represent uncertainty, for instance, in our weather forecasting systems using singular vector perturbations or like ensemble data assimilation perturbations that tries to capture that uncertainty at the start of the forecast. But then we also represent uncertainty in our model formulation using stochastic perturbations. So those are random perturbations at every time step given to the physics tendency in the model. So we have this cloud of forecasts that are integrated forward in time, and then you add this stochastic perturbations that represent uncertainty in your subgrid scale tendencies. And eventually we want a forecast ensemble that represents both the mean, the best mean ensemble mean, but also the best spread in your ensemble, or the PDF of your ensemble. So currently in forecast systems, this stochastic component, or the model error component, is represented using two different mechanisms, or two different formulations. This has been developed over the last two and a half decades, mainly first implemented at ECMWF, the European weather forecasting system. And now I think most weather forecasting systems do use a stochastic scheme in their ensemble forecast. Judith Berner has written a really good review paper about stochastic parameterization and why it's important both for weather and climate models in 2016. So the current most commonly used stochastic parameterizations are these two versions. One is the stochastically perturbed parameterization tendencies, or SPPT. That's used in the ECMWF system. Also, a similar formulation is used in the US ENSEMBLE system, the Japanese system. And then there's also the stochastic kinetic energy backscatter scheme, which represents upscale error growth or upscale transfer of kinetic energy, which there was discussion about earlier today as well. So the stochastically perturbed parameterizations tendencies, or the SPPT, that is implemented in terms of perturbing the physics tendency in the model. So at every time step, you do the dynamical integration, and then you do the all the different physics schemes such as gravity wave drag or convection, radiation. All those schemes generate a tendency in temperature, moisture, and the winds, horizontal winds. You take those tendencies and you do a multiplicative noise perturbation. So 1 plus a random perturbation times your physics tendency. That will be your modified physics tendency at that time step. And that's then further integrated down in the model, where that goes into the next dynamical time step integration. So there's a lot of work over the last decade. I've just highlighted two papers here, but there are many other papers that have looked at the impact of these stochastic physics schemes on both weather forecasts, improving the reliability of weather forecasts, as well as climate timescale. So I'll be talking about another way of representing uncertainty in our systems, which we tried, and compare them to the SPPT formulation that I just described. So what we did was we had a super parameterized model, the ECMWF IFS, integrated forecasting system. So the super parameterization is implemented in the similar way as SPCAM that Alistair talked about as well, where we have an embedded cloud resolving model within the grid cell of the global model. So what we want to do is to generate subgrid scale uncertainty. So we perturb the cloud resolving model only at the initial time step in this formulation, and then we let an ensemble of simulations run forward. The large scale is exactly the same at the initial condition. The subgrid scale is perturbed at the initial condition. And then we run an ensemble, a 21-member ensemble from this simulation, and then look at how the error growth in that system compares to a SPPT system, which is a stochastic physics perturbation. The case I'll be presenting today is the atmospheric river example, which is just an event basis. So here there was an extremely extreme event, atmospheric river, that impacted northern UK in Cumbria region, which is over here, in 2015, where it brought record floods, and it was caused essentially because of this cyclone, extratropical cyclone that was also accompanied by this atmospheric river, a lot of integrated vapor transport in the atmosphere. that brought in water vapor into the highlands in northern UK. So we looked at forecasting this with the ensemble, with the what's currently used, the SPPT, stochastic physics perturbations, and then the ensemble superparameterization, which is plotted on the right. What's plotted here is the integrated vapor transport, which is integrating water vapor times the wind velocity, the horizontal wind velocity through the atmospheric column. And the middle column is the reanalysis IVT, integrated vapor transport. And we are comparing how the forecast of this atmospheric river looks like at 6 days out and then 6.5 days out. In the reanalysis, we have this really strong IVT, or integrated vapor transport, that makes landfall into northern UK. And in the SPPT, we have this atmospheric river event, but a muted signal in the IVT. In the superparameterization, we see a stronger case of integrated vapor transport coming in. It's still weaker than the reanalysis, but it has a higher amount of integrated vapor transport as well as precipitation, which I'll not show today.
Atmospheric rivers, I think of atmospheric rivers as being something which is mostly on the resolved scale. And so I was curious why this is a good demonstration of the value of stochastic parameterization.
Yeah, that's a great question. So the large scale vapor transport, I think, is resolved, but there have been other studies as well which show that the convection within atmospheric rivers feeds back to how much water vapor is carried. And if it's, especially if the model has a drizzle problem where it's continuously raining out, that would take out the water vapor, right? And I think that's what is happening, where SPCAM has been shown to have less of a drizzle problem, where it's less sensitive to moisture and rains out less. So it keeps that water vapor in the atmosphere so that it can be carried. So I'll switch now to the machine learning part of the talk, which some of it is related to atmospheric rivers. But first, I'll talk about machine learning for stochastic parameterization. This is work David John led. I was a collaborator on this paper, where we looked at, can we do machine learning just in an idealized setup in the Lorentz 96 system, but in a 2-scale Lorentz 96 system. So we have the X variables and then a second layer, which is a set of Y variables. And a number of these Y variables are coupled to each X variable. So you can think of this as your X as being the large scale, GCM scale, and then the Y variables are your small scale, subgrid scale variables. And then a sum of a number of Y variables act as forcing for your X variable. And the Y variable is integrated through this equation, where a single X will force a number of Y high frequency variables. So what we were trying to do is, if we represent this forcing from your Y grid or your Y variable in the system as a subgrid scale U of X, so it's a subgrid scale tendency that's given to your X variable, can we run a machine learning algorithm on this, on a truth simulation where you're running the full 2-scale system, and learn the forcing that Y should give to X, but learn it in a stochastic way, that it's representing both the mean but also the uncertainty, or the PDF of the U that should force X. And this is the machine learning algorithm we chose, was the generative adversarial networks, or GANs. So the way GANs work is, you have two different neural nets within them. One is called the generator, which creates synthetic samples drawn from a training database data based on this latent vector, which is your input vector. And this synthetic sample is then given to your critic or your discriminator network, which then tries to determine if the sample is from a true distribution or not. So it's fed the true samples as well. And that's then fed back to the generator network, which is optimized then to generate better synthetic samples. So in our case, an example is our latent vector can be the x at the previous time step, the subgrid scale forcing at the previous time step, and then some kind of noise. Like here, the example is the AR1 noise. And then it's supposed to generate what's the subgrid scale forcing at the next time step, so U of t. We tried many different configurations with GANs, which are quite sensitive to the training and how we train them and what input is given into GANs. What I'll be showing is results from these many different configurations, and we could do this only because of the idealized system in Lawrence 96. It's probably impractical to do this with even with a QG model, I think. But so we tried giving the input both x and u at the previous time step, or just giving x at the previous time step, which is your large scale state. And then the noise that we gave it, we gave it a large noise, a medium, small, and a tiny amplitude for the noise term. And then we also gave it white noise or red noise forcing, so either correlated in time or not correlated in time. So what we show in this paper is there are configurations of GANs where we can, so what's plotted here is the root mean square error and the spread in the model. So what ideally we would want is the root mean square error to be small as possible, but the spread to match the root mean square error of your ensemble. So that would give you a reliable ensemble. And there were configurations of GANs which beat polynomial parameterization, which is really hard to beat in this simple system. A simple polynomial parameterization does really well. But in a weather forecasting setup with 750 initial conditions, 50 ensemble members, we do show that a few configurations of GANs with the small noise terms can beat the polynomial parameterization in this Lawrence 96. And the same configurations also do well in your climate forecast. So for the climate forecast, we compared the PDFs of the distribution. So computing a Hellinger distance or a PDF of the climate state from the true PDF of the system. And even there, the same configurations had a better Hellinger distance, so a better climate state and a better ensemble weather forecast in this setup. So it's promising, but it's challenging to do with more complex systems. And I would love to chat with anyone here on exploring this or other methods for stochastic parameterization with machine learning. So now I'll present results on using on doing post-processing, which is not parameterization, but trying to correct model forecasts, but with machine learning methods. So what we used here were CNNs or convolutional neural networks. It's work led by an excellent grad student, Will Chapman, who will soon be graduating and joining M2 Lines as a postdoc. So here we looked at using CNNs to correct forecasts of integrated vapor transport, so atmospheric rivers, specifically in the Northeast Pacific. And I'll probably not go into details of the CNNs. All of you must be familiar with this, but we optimize a certain cost function to get the hyperparameters of the CNN. The question we were asking is, can we use these modern deep learning networks to act on image data of integrated vapor transport to improve or post-process these forecasts? And the reason is traditionally what's used is called model output statistics, or MOS, to be concise. And those act on point-based forecast. So they take every grid point or just point-based data and they improve the statistics of those grid points. Whereas CNNs or these networks, they can also look at a spatial map to correct your forecast or to do post-processing. So that's an advantage compared to what's traditionally used for post-processing, so that bringing in non-local information in post-processing your forecasts. And then once it's computationally probably more expensive to train your machine learning method than like Moss methods or regression or bias correction. But once you have a trained network, it's much cheaper to run and post-process. So what we were looking at is atmospheric rivers in the Northeast Pacific, looking at the ENSEMBLE forecast, so the US National Forecasting System. Can we improve their forecast further using machine learning post-processing? So these atmospheric rivers are these long plumes of water vapor that bring a lot of rainfall into Western US, also Western Europe and other regions around the globe. They do have a lot of, they do make a lot of damages like tropical cyclones or hurricanes as well, especially the extreme and exceptional atmospheric rivers. The damage can be up more than tens of millions or hundreds of millions of dollars. And they do contribute a lot, like in some regions, more than 50% of the annual precipitation comes from these atmospheric river events. So the way we identify them is using integrated vapor transport as one of the variables, or we can also use integrated water vapor. And currently the error in atmospheric river forecasts out to 3 days can be quite large. There's just a graph from a paper in 2013, Wick et al., that shows that out to 3 days, the forecast error can be up to 400 kilometers in terms of where they make landfall. So that's a huge error in terms of impact. So what we did was to train just a CNN on a deterministic forecast first. So this is a result from post-processing, just deterministic forecast from the GFS, the Global Forecasting System from ENSEMBLE. And what I'm showing here is forecast out to 96 hours, so like 4 days. So what's plotted here is the percentage improvement in the root mean square error of a neural network post-processed GFS forecast, where overall in the entire domain, we show improvement in most regions with this neural network post-processing. This is a published paper. So yeah, further, after doing the deterministic forecast, the next work we did was to try and do this in a probabilistic setup. So it's a recent paper that I think is coming out. It's released online. It's not fully published yet. There is a DOI for it, monthly weather review. So we used the MSE, the mean square error, to do the deterministic correction to just give one post-processed output. And then further, in this work, we used also the continuous rank probability skill score. So that's CRPS, which is the probabilistic measure of error in your output. And we can use this as a loss function to optimize to get both the mean and the standard deviation of your output. So that's post-processing and ensemble, even if the input is just a single variable or it's a deterministic forecast. I'll not discuss about the ELB or the elbow loss function. We tried Bayesian neural networks, but we are not yet successful in doing that. Yeah, if there's interest, it would be great to chat about that. So the idea is you want a good ensemble forecast that both, like I mentioned, predicts the mean, but also the uncertainty in your forecasts. And we want the spread of the ensemble to capture the observations, which gives you a reliable forecast. So this is an example of where the forecast can be unreliable, where if your observations are at the edge of your what's known as the rank histogram, so it ranks your ensemble. If it's underdispersive, which means if the spread is much lower than the error in your ensemble, then the ensemble, the observation is outside your model. Your model trusts itself a lot more than the error that's present in the forecast. So this is an underdispersive ensemble, which is not great. So what we did, the first work was just doing the deterministic forecast using the mean square error loss, and we show that we can bias correct or improve the mean forecast. And the second work is doing the probabilistic forecast correction, which is correcting both the mean and the standard deviation in your forecast using the CRPS loss. And we tried this, in the interest of time, I skipped the details, but we tried this by running this on an ensemble regional model and compare it to the global GFS, the ENSEMBLE ensemble forecast system. And the verification was done with the NASA reanalysis, the MERA2 reanalysis system. We tried a few different configurations. So a neural network that just a simple neural network, a CNN, and also an analog ensemble, which is not, it's not using neural networks. It's trying to generate analogs from previous historical forecasts. So in these forecasts, what we saw was that doing the neural network probabilistic correction, we can get a more reliable ensemble where your rank histogram is flat, which is good. If the rank histogram is flat, it's not over dispersive or under dispersive. Whereas the regular GEFS, which is the ENSEMBLE forecast system, is under dispersive in the forecast. Yeah, so there's another paper, Sue Ellen Haupt led the paper. Will Chapman and I are co-authors on this, where we discuss post-processing and different post-processing methods with machine learning and why it's important. So now in the last few minutes, I'll discuss work led by Tim Higgins, who's an excellent grad student in my group at CU Boulder, where we are trying to use machine learning for an identification problem of atmospheric rivers, so a segmentation problem. So what we are trying to do is, if we have a really giant data set, running traditional detection methods or image recognition methods is too expensive. So can we use machine learning, especially semantic segmentation methods, to detect these extreme weather events? So there's been a lot of work done by Karthik, Prabhat, and others from Lawrence Berkeley. We are deriving from that as well, working with Karthik and group on that. The data set we are using is the weather at home data set, which runs climate models on people's CPUs, clock cycles when the machine is sleeping. And so we can get hundreds of ensembles for the present climate and future climate scenarios at high resolution. So we are looking at a 60-kilometer resolution model here with hundreds of ensembles, which is unprecedented. And so there's work done, like I mentioned, from the Lawrence Berkeley group, Prabhat et al. 2020. They discussed using this DeepLab V3 network to identify atmospheric rivers and tropical cyclones. It's a really good detection method, but it is expensive to run, and running it on a large ensemble, a large data set, is expensive. So there's work more recently done in collaboration with Karthik as well from a group in Switzerland, where they use this context-guided CGNet network, which is much lighter, but it does a similar detection method, a semantic segmentation method, to detect atmospheric rivers or tropical cyclones. So Tim has been working with them to improve their method to work on different domains. It was trained only on global domains so far. And the problem is to identify atmospheric rivers if we are given just a map of integrated water vapor. So we don't have integrated vapor transport because of the way the global model was run on people's machines. So the output is really light in terms of the variables that we get back. So we use this CGNet, which has been previously used in cityscapes and other identification problems. We use the same to detect atmospheric river features in integrated water vapor maps from these ensemble forecasts. So we have tried this in few different configurations, a global domain, a large domain that captures both the Pacific and the North Atlantic, and then a small domain, which is just the Northeast Pacific, and then the final domain, ArcMap, is a project where they compare many different detection methods for atmospheric rivers, and we compare our machine learning method with theirs as well, with the traditional algorithms. The metric we use is this intersection over union. So when does our method of identification overlap with other methods compared to a union of the footprints of these different methods? So Tim has compared this to many different atmospheric river detection methods, which are all labeled here on the bottom from many different groups around the world. And the three different configurations of the CGNet detection are on the right. What we see is that CGNet has a similar IOU consistency with the different ArcMap algorithms, which use integrated vapor transport. And it also does best when the training domain is similar to the detection domain. If we change that resolution or domain, then there's a degradation of the skill. And then we are looking at how it performs in the current climate and then compare it to what happens in the future climate. So he's run this on hundreds of ensemble members, or more than 100 ensemble members for a current climate that's been run for a decade at 60 kilometers. And then this is the distribution of the number of atmospheric river events per month in the Northeast Pacific region, and comparing it to the reanalysis occurrence in the present climate. It mostly captures the reanalysis, but with a wider distribution in the present climate because of these 100 ensemble members. So it shows how wide the distribution could have been for atmospheric river occurrence. And then we look at what happens in the future in terms of change in atmospheric river activity. This is my final slide. What we see is the atmospheric river activity, especially in the subtropics, as well as in the higher mid-latitudes, increases. It mostly increases everywhere, but there's a higher increase in the subtropics, so affecting Southern California as well as affecting the Pacific Northwest. There's greater activity in this large ensemble. And we haven't yet diagnosed whether this is because of increased moisture, which is definitely true. In a warmer world, we have more moisture in the atmosphere, or there's also changes in circulation with the Hadley circulation changing or mid-latitude jet stream shifting. Yeah, so that's some work we're doing right now with this large data set. So with that, I'll end with these concluding remarks. So biases in the mean and variability of tropical precipitation is reduced in stochastic prediction models, weather and climate timescales, extreme events. They've been shown that a lot of stochastic models do represent extreme weather better. And then we have tried machine learning methods to improve forecast, post-process forecasts, as well as these identification of extreme weather events in climate simulations. Thanks.
Questions, sorry.
Great work.
So you mentioned something about using the Bayesian neural network to do the UQ versus the elbow method. I'm wondering if you can elaborate a bit more about what you found.
Yeah, this is probably a conversation of over coffee, I guess. Like, so Will Chapman, we tried with Bayesian neural networks, if we can derive like the PDF, if the hyperparameters are PDFs, can we derive a better probabilistic forecast or a better ensemble forecast output from that kind of a network? It's quite sensitive to how you train it and how you tune it. So we haven't yet been able to optimize it to get a better probabilistic forecast with the Bayesian neural nets. So, but yeah, it's a conversation. I haven't tested it a lot. I've seen a lot of work more on the computer science side, Yaren Gal and others who have developed Bayesian neural nets for computer science applications. I haven't seen much done in our field in terms of probabilistic forecast, right? And it's quite sensitive, I think, to how you train it and the input.
I have a question from Judith Werner, who is online. Could you comment on how machine learning can be used to identify systematic model from random model errors?
She can answer this better than myself. Yeah, that's a good question. I think we can definitely try and do this, where we know that our model has systematic biases, or there are biases in the mean state of the model. Currently, we use simple statistics like looking at the mean over a long period and then comparing it to reanalysis. But with machine learning, we might be able to capture like the nonlinear part of those biases. That's not only the mean state, but it could be nonlinear in terms of where the biases are coming from. And those are part of the physics parameterizations, or the error in the configuration of the model. Whereas we actually have random error in chaotic systems that cannot be improved by just improving physics, and that needs to be identified. I don't know how well we can do this with machine learning. If we can identify the the physics error or the model error part, then maybe the other random error part can be represented accurately with stochastic physics. Yeah. But yeah, maybe Laura or Judith or anyone else has comments on how to do this better. Okay. Yeah.
I think it's something for a longer
conversation. Yeah. Judith, you should be here for dinner or coffee.
She just answered no.
It was a real question. I don't know how to do it either.
Yeah.
Sorry. Yeah, that was phenomenal. Thanks, Anish. So back to the work where you actually try to correct the forecast. So, I mean, can you give us a little bit more detail? Because that's pretty exciting, right? You still are using the full forward model.
Yeah.
But basically kind of adding on top of that, a way to correct.
Right? Exactly. So the post-processing of, so the one by Will Chapman, you mean? Yeah. Yeah, so here what we do is, so the dynamical model is generating forecasts. So it generates a field of like integrated vapor transport. And then we have reanalysis that shows that this integrated vapor transport has error in the forecast, right? So then we can compute the model minus reanalysis, or we can, so what we did was to give your neural net, your CNN, the model forecast at day 2, let's say for an example. So we give the input day 2 forecast of your integrated vapor transport field. And then the output during the training should be the reanalysis integrated vapor transport. So your neural network is optimized to convert your forecast field to your reanalysis field. So once you do this, in real time, if you get a model forecast, but you don't have reanalysis because you're doing forecasts in the future, right? You can run your neural network to generate a field that should be close to reanalysis because of the way it's trained. So that's what we call as post-processing, where the dynamical model is generating a forecast. You train your neural network to convert that forecast into reanalysis based on historical reanalysis. And then in real time, you can run the same neural network to correct your forecast towards,
There's no feedback.
There's no feedback currently, yeah. I mean, you could do feedback, I guess, if you do it long enough that.
Yeah, depending on the time window, right? You
Yeah, exactly. And you can, we trained only one neural network, but you could train different neural nets for different lead time of the forecast.
Great, thanks. Any final question, Aneesh? Yes, please.
This might be a very naive question, but you're trying to predict landfall. Have you tried to predict just whether or not you're going to have an atmospheric river going toward the Western United States?
So here, we did not predict landfall. Actually, we predicted the total integrated vapor transport field. I mean, that would probably be a simpler problem if you have integrated vapor transport above a threshold or not, rather than correcting the whole IVT field, just do a threshold-based correction. We haven't tried it, but yeah, maybe it'll do even better if you just try that, right? But yeah, great question. Thanks.
Okay. Thanks again, Aneesh.
Thank you.
Thank Aneesh again. It was a great talk.
Thanks.